Hello everyone, welcome back to our channel. Let's discuss the next topic in the NMR spectroscopy. Okay, so before going to discuss about the next topic, let's see the effect of the electron cloud around the nucleus. So in the principle of NMR spectroscopy, we had a clear discussion that precisional frequency, that is generally represented by what? Gamma L. Precisional frequency gamma L is directly proportional to what? Strength of the external magnetic field. Right? We know that if we increase the strength of the external magnetic field, Fresnel frequency of the nucleus will be increases. What is the Fresnel frequency? The number of rotations performed by the spinning nucleus around the external magnetic field in a given time. How many number of rotations are performed by your nucleus? That number in a given time is commonly called as precisional frequency. Suppose whenever the nucleus is associated with electron cloud, what will happen? So what the people are saying, see this, precisional frequency is indirectly proportional to the electron density or electron cloud. It means if the nucleus is surrounded by the electron cloud, the precisional frequency of the nucleus will be decreases. By increasing the electron density, the precisional frequency value is going to be decreases. Why? What is the reason? The reason is, see this one. Here we have a nucleus. The nucleus is surrounded by what? Electron cloud. So whenever the nucleus is surrounded by the electron cloud, what will happen? The electron cloud will undergo induced circulation and produces new magnetic field, that is commonly called as induced magnetic field or secondary magnetic field. What is happening? Whenever the nucleus is associated with the electron cloud is going to create new magnetic field. That magnetic field is commonly called as a secondary magnetic field. The produced secondary magnetic field opposes the direction of external magnetic field. See this one, this is the direction of our external magnetic field, right? So this is what? Newly produced magnetic field because of the electronic circulation. So what is happening? Whatever the induced magnetic field is produced, that is going to oppose the strength of the external magnetic field. Suppose assume that if the strength of the external magnetic field is 1.41, the produced secondary magnetic field is 0.01, then the net field experienced by the nucleus is what? 1.40. It means whatever the external magnetic field we are taking, that is not going to approach your nucleus directly because of the formation of this internal secondary magnetic field. So net field at the nucleus is decreasing or not? So strength of the magnetic field at the nucleus decreasing means automatically what happens? The precisional frequency will be decreases. So in case of the isolated nucleus, what happens? There is no induced magnetic field. There is no chance for the induced magnetic field. That's why what happens? Whatever the field you will take from the external mode, that strength is directly going to approaches the nucleus. That's why whenever the nucleus is associated with some electron density, what will happen? The precisional frequency of the nucleus will be decreases. This is the underlying point. Okay, see this one. Here are some examples. CH2 is there. This is one set. This is another set. So if you talk about the precisional frequency of these two protons are going to be higher. Why? Because the chlorine is directly connected to what? CH2 or not? That's why because of the minus psi effect, what happens? The complete electron density move towards the chlorine. So these bonding electrons are moving towards the chlorine, means at the carbon electron density is decreasing or not. So at the carbon electron density decreasing means the CH bonding electrons move towards what? Carbon or not. That's why at hydrogen the electron density will be decreases. Electron density decreases means what? Strength of the magnetic field increases. So precessional frequency will be increases. Okay, that is the thing. So that is the thing which we have given here. Nucleus which is associated with electron cloud, once placed in the external magnetic field, what is happening? It undergo induced circulation, produces new magnetic field, is commonly called as a secondary magnetic field. Okay, the directions of the secondary magnetic field opposes the strength of the external magnetic field. That phenomena is commonly called as what? Diamagnetic phenomena. Whenever two magnetic field opposes, what will happen? There will be a mutual cancellation of the fields. Therefore, induced magnetic field cancels the applied magnetic field. Net magnetic field at the nucleus is lesser. That's why smaller precessional frequencies. Okay, so whenever electron cloud at nucleus decreasing, net field is going to be more extended cancellation of the applied fields. Net field at nucleus at smaller decreases the precessional frequency. Simply the concept is, if the nucleus is surrounded by electron cloud, the net precessional frequency of the nucleus is going to be lesser. That is represented in this way. Effective field at the nucleus equal to strength of the external magnetic field minus strength of the induced magnetic field. So this one, induced magnetic field, is also directly proportional to H naught. So if you remove the proportionality, we should write a constant that is commonly called as shielding constant. So substitute this value in this equation. What will we get? H naught minus sigma into H naught. So H naught is common, then you will get H naught into 1 minus sigma. So the net field experienced by the nucleus can be calculated by using this phenomenon. Okay, so the decrease in the precessional frequency of the nucleus due to the electron cloud is commonly called as shielding effect. It is very, very, very important. What is shielding effect of the nucleus? What is the shielding effect? Whenever the nucleus is surrounded by the electron cloud, that nucleus once placed in the external magnetic field, what happens? The electrons will undergo induced circulation and produces new magnetic field, is commonly called as a secondary magnetic field. The secondary magnetic field opposes the direction of the external magnetic field. That's why the net field at the nucleus is going to be decreases. Because of the decreasing the net field, the precessional frequency of the nucleus is going to be decreases. This phenomena is commonly called as shielding effect. The strength of the shielding effect is measured by what? Shielding constant, that is sigma. Sigma is higher means the precessional frequencies are lesser. Okay, already we know that NMR equation from the classical approach, gamma L equal to gamma into H naught by 2 pi. Okay, this is in case of what? Isolated nucleus. There is no electron density. Suppose if the electron density is present, what happens? The strength of the external magnetic field is replaced with what? Net field or not? So here we have calculated net field, that is H naught into 1 minus sigma. The substitute that value here, you will get this one. The reduced precessional frequency of the nucleus due to the presence of electronic cloud can be calculated by using this formula. Okay, I think you understand. Simply remember one thing: whenever the nucleus is surrounded by the electron cloud, the precisional frequency will be lesser. Only this point you should underline. Okay, so this is the general topic which we need to understand before going to discuss about very important topic, that is chemical shifts. In NMR spectroscopy, the main topic is chemical shift. If you know the chemical shift, you can easily determine the structure of unknown chemical compounds 100%. Generally, what we will do, we will use four different techniques for the structural determination of organic compounds. What are those? UV visible spectroscopy, IR spectroscopy, NMR spectroscopy, and mass spectrometry. If you are perfect in NMR spectra, 99 percentage chances are there you can identify easily the structure of compound without using the data of UV, IR and mass. That's why put a complete focus on the understanding of chemical shift values. Okay, let's see the example. See, here you have one molecule, two carbons are there, the two carbons are connected to two hydrogens, the remaining bonds are connected by X type atoms. Assume that X means chlorine. Here assume Y means bromine. So here chlorines are there, here bromines are there. So if two different atoms are present, what happens? These two protons will be considered as different or not? So H1 and H2 are chemically non-equivalent sets of protons. Am I clear? We have one hypothetical molecule. In the hypothetical molecule we have different connectivity. That's why both protons are chemically non-equivalent. If the protons are chemically non-equivalent, what will happen? They will give two different signals or not? Assume that every nucleus is going to have some precisional frequency or not? Okay, assume the H1 nucleus precisional frequency is this much, 60 0 0 0 0 80 H. The H2 precisional frequency is this much, 60 0 0 0 100 H's. Okay, if we compare these two in hypothetical molecule, we have written in this way. This is 80, this is 100. It means that what? H1 precisional frequency is lesser than the H2 precisional frequency. Why? H1 Fresnel frequency is associated with a large electron cloud. H2 nucleus is associated with lesser electronic cloud. That's why H1 Fresnel frequency is lesser and H2 Fresnel frequency is more. Now what we are doing? We are sending radio frequency radiation on this molecule. Thereby what happens? The radio frequency radiation continuously send the energy in the form of frequency or not. So it is starting what? 60 0 0 0 0 0 0 Hz, 01 Hz, 02 Hz, 03 Hz, 04 Hz, 05 Hz. Continuously the radiation is going to be produced at the different frequencies. So whenever the frequency reaches to this frequency, what happens? Resonance condition takes place, so you will get the signal. Similarly, whenever the radio frequency radiation matches the Fresnel frequency, what happens? We will get another signal. Okay. So for this molecule, we are getting how many signals? Two signals or not? Okay. For H1, one signal, and for H2, one signal. Am I clear? We have one hypothetical molecule. Hypothetical molecule, we have two different protons. So two different protons are giving two different signals. Okay. Suppose assume that if we have 100 different protons in the molecule, if you have 100 different protons like the 100 different protons are there, means we will get 100 different signals or not? So each and everyone having this type of frictional frequency. Assume that 60 0 0 0 80 Hz, 60 0 0 0 90 Hz, 60 0 0 0 95 Hz, 60 0 0 0 100 Hz, 60 0 0 0 102 Hz, 60 0 0 0 0 103 Hz, 105 Hz. Like that we have different signal. Is it possible for us to draw the complete spectra in this particular notebook? Is it possible for us? See this. For two peaks, we are using this much space. If you have 100 peaks like these values, is it possible to put all the signals in this small space? No, it is not possible. It means whatever the representation here we are giving, the representation is not unique in nature. It is not valid for us. Why? Because in chemical system, if you take proteins, if you take polymers, what happens? We will have different kinds of higher number of different nucleus or not. So at that time, if you record the spectra, how can we record the spectra? For that purpose, we are having the topic called as a chemical shift. Okay, so in order to simplify the spectra, what we are doing, see this. Let us take Z. We are taking one another nucleus. The precisional frequency of that nucleus is fixed as 60 megahertz. Okay, see this. Here you have two signals, na? One is at 60 Hz, one is at 60 100 Hz. What I am doing, I am taking one reference, okay, that is represented as Z. I am fixing that the precisional frequency of that nucleus is 60 Hz. And considering the peak of that reference is 0. If we consider that that is 0, if 60 megahertz is 0, then what will be the value of this 80 Hz? 60 that will become 80 or not? Then 60 100 will be converted into what? Simple 100 or not? It means what we are observing? Simplification of the values or not? We are going to the relative numbers, not the original numbers, by placing a reference. I think you can understand. Okay. So in order to simplify the spectra, what we are doing while recording the NMR spectra of any compound, what we are doing, we are adding some compound, that is X. This is commonly called as a reference standard, otherwise standard reference. So we are having some standard reference. In the standard reference, we will have protons. The proton will give a single signal. Okay, that single signal is going to be considered as what? Standard one. That standard one is represented as 0. So with respective to that standard, whatever the signals we will get for remaining protons, that can be taken with respective to the signal of the jet. Thereby, our spectra is going to be simplified. Okay. Then, what is the chemical shift? We are talking about the chemical systems or not? By placing the standard, what is happening? There is a change in the number or not? This number is what? Precisional frequency or not? This is the precisional frequency of H1. This is the precisional frequency of your standard proton. Right? By subtracting these two values, the precisional frequency of H1 and the precisional frequency of the standard, 80 minus 0, you will get what? 80. 100 minus 0, you will get what? 100. Otherwise, you can say 60 minus 60 H. The difference between the precisional frequency of sample proton and precisional frequency of what we call it as reference proton is getting the peak value or not. That is commonly called as a chemical shift. See this one. Difference in the absolute precisional frequencies of sample protons and reference protons are commonly called as chemical shift. See, the values are in Hz or not. That's why chemical shift in Hz equal to Precisional frequency of the sample proton minus precisional frequency of the reference proton. This is commonly called as chemical shift value. This can also written as absorption position of signal in the NMR spectrum is commonly called as chemical shift. Otherwise, we can say shift in the edges away from the reference or away from the standard is commonly called as chemical shift. So, from the standard, what is the value which is away? That is 80. So, 80 is the chemical shift of the H1. So simply chemical shift has been introduced to reduce the complexity of the spectra. So in order to reduce the complexity of the spectra, what we are doing, we are adding some external substance to the sample while recording the spectra. The external standard, commonly called as reference standard, is going to give a certain peak that will be considered as the standard one, considered as 0. With reference to that standard, whatever the peak you will get, that is minus in nature. Okay, so what we are observing, the shift we are getting, that is in the form of hedges. But here is a problem. What is the problem? See this. Suppose we are using the external magnetic field strength of 1.41. You need to remember the what we call it as principle of NMR. What is the principle? Whatever the sample we are having, that sample is going to place in the external magnetic field, right? Classical approach here we are talking. Once the nucleus is placed in the external magnetic field, what happens? Precision phenomena takes place. You will get the precisional frequency. Then you can compare the precisional frequency with the radio wave. Then you will get the spectra. So everything we have discussed in the previous video. Okay. So what is the concept? Here we have the molecule. In the molecule we are having two different protons. So the first proton precisional frequency is this one, the second proton precisional frequency is this one. Okay, while recording the spectra of this molecule, we need to add one reference compound. The reference compound containing nucleus, the nucleus precisional frequency is 60 megahertz. That is placed in the strength of external magnetic field, that is 1.41. So according to the formula, the chemical shift of H1 equal to this precisional frequency minus this precisional frequency, thereby we are getting 80H. Similarly, chemical shift value of H2 equal to precisional frequency of H2 minus precisional frequency of reference. So you will get 100. So we are getting two peaks, at 81 peak, at 100 another peak. So this is perfectly alright. Already we know that the precisional frequency of the nucleus is directly proportional to the what? Strength of external magnetic field or not? So if you change the strength of the external magnetic field, what happens? The precisional frequency of the nucleus will be changes or not? So see this here, what I am doing, I am increasing the strength of the external magnetic field. Simply I have doubled the strength of external magnetic field. Initially 1.41, double means 2.82 or not. So the same system I am going to place it in double strength. Double strength, see this 2.82. Then what happens? According to this formula, the strength is going to be double or not? So precisional frequencies are going to be double or not? So see this, here it is 60 80 Hz. So it should be double means what? 120 160 Hz. Here it is 100 means 120 200. Here it is 60 means it is 120. So all the precisional frequency are doubled when increased the strength of the external magnetic field. Thereby calculate the precisional chemical shift. So the chemical shift of H1 equal to what? 160 minus this one. So you will get 160. 200 minus this one, you will get 200. So what you are getting? You are getting two peaks, but what are the values? Here it is 160, here it is 200. But in this case 80 and 100. You have the same molecule, Both the nucleus are same, but by changing the strength of the external magnetic field, what is happening? The chemical shift value is going to be changed or not? So this is inconvenient for us. So what is inconvenient? The chemical shift value of the proton in terms of the edges is inconvenient. Why? If you change the strength, the chemical shift value is changing. The chemical shift value should be always unique in nature. It should be a single value and separate value for each and every proton. But if you take in hedges, that is depending upon the strength. See this chemical shift value in hedges depending upon the strength of the external magnetic field and also instrumental frequency. That's why it is not convenient for us. That's why we need to fix the chemical shift value for each and every proton. That's why one needs chemical shift independent on strength of the external magnetic field or independent on the instrumental frequency. That's why the people are introduced two scales. What are those? Delta scale and tau scale. Most common scale is the delta scale, less common scale is the tau scale. Delta is represented like this, tau is represented like this. So in this case what we are doing, see this, same, the reference system is there, same molecule, the placed in what? External magnetic field of double strength. But now what we have done, we have fixed the instrument frequency. So what the people are saying, whatever the formula you have, the precisional frequencies of the sample protons minus the precisional frequencies of the reference protons is commonly called as chemical shift or not. What the people are suggesting, simply divide these values with the instrumental frequency. Whatever the instrument you are using, the instrument is going to have some particular frequency na. Simply divide your chemical shift with the instrument frequency. See this one, in the first case we are getting 80 na, in the first case at 1.41 tesla. See this, at 1.41 tesla, 80 na, 80 divided with instrument frequency, we have fixed the instrument frequency, that is 60 megahertz. We have fixed the instrument frequency 60 megahertz. So 80 by 60 1.33, 100 by 60 1.66 at 1.41 tesla. The same situation we are taking at 2.82 tesla. If you double, automatically everything is double na. So 160 by this way, this is 80 na, 80 become 160, so 60 become 120, so 160 by 120, what happens? 1.33. This is 100, will be 200, this is 60, will be 120, will become what? 1.6. You see this one, by dividing the value with the instrument frequency, by changing the strength of the external magnetic field also, chemical shift values are not changing. Now chemical shift values are become independent or not. That's why the delta scale is equal to precisional frequencies of the sample protons minus precisional frequencies of the reference protons divided with instrument frequency. This is the real definition of the chemical shift. Okay, so here it is taken in megahertz, right? The megahertz can be converted into simple hertz. So if you remove the mega, it will become what? 10 power 6 into ppm. This is the previous definition or not? That's why chemical shifts in hertz by gamma I into ppm. This is also previous definition, hedges of frequency away from the reference by gamma I. So in terms of the magnetic field strength, we can write in this way. Okay, now the delta chemical shift values are independent on the strength of the external magnetic field. The same thing here we have discussed. For clarity purpose, here see this one. This is rough in nature, no? Here this is proper in nature. Okay, similar thing. So what is the relation between delta and tau? Tau equal to 10 minus delta. It means delta plus tau equal to 10. Simply remember like that. Whatever the delta values you will get, simply subtract from the 10, you will get the tau values. Okay. So here we are discussing that we need to use one reference. So what are the chemicals which can be used as a reference? This is very very important point. In terms of the interviews, the people will ask you what are the references which we need to take while recording the NMR spectra. You should say two molecules can be used. One is tetramethylsilane, the second one is 3-trimethylsilyl propane 1 sulfonic acid and its salts. In most of the cases we are taking tetramethylsilane only. That is most common one. Why tetramethylsilane? See this one. In case of tetramethylsilane, we are having how many protons? 3 plus 3, 6. 3 plus total 12 protons are there. So 12 protons are chemically equivalent or not? Why? Because environment is same. That's why 12 protons are same in nature. That's why considered as one set. So 12 protons will give only one signal. Okay. If you see the electron density at the proton, already we know that electron density increases. What happened? Here it is very very important point you need to remember. If the strength of the external magnetic field increases, what will happen? Precessional frequencies will be increases. Precessional frequencies will be increases. If the precessional frequencies increases, the delta chemical shift values will be increases. This is the fundamental thing which all the students should understand. Okay, by increasing field strength, precessional frequency increases. By increasing precessional frequency, chemical shift value increases. This is the standard line everyone should remember. Okay. If strength of magnetic field decreases, what happens? Precessional frequency decreases, thereby chemical shift value decreases. See this one. Here we have silicon and carbon. If you compare carbon and silicon, which one is more electronegative? Carbon is more electronegative or not? That's why what happens? These carbon silicon bonding electrons always move towards what? Carbon or not? That's why the electron density at the carbon increases or not? So at the carbon electron density increases means automatically electron density at the proton is increasing or not. So electron density at proton is increasing means net magnetic field is decreases or not. Net magnetic field decreases means precessional frequency decreases. So delta chemical shift values are decreases or not. That's why whatever the signal you will get, always this signal is going to be at the lesser end of the spectrum. This is the first advantage. The TMS protons are highly denser in nature. That's why the precessional frequencies of these protons are very less. So the delta chemical shift values of the tetramethylsilane protons are very less, always considered near to zero. Okay. So what is the second advantage? TMS having only one equivalent sets of protons, so show only one signal in the spectrum. Okay. This is due to the lesser precessional frequencies than the sample protons. Delta chemical shift values sample protons are higher in range. So all the protons are inert. TMS is an inert chemical. It cannot react with any sample. That's why what happens? Interference is not possible. So it is readily soluble in all organic solvents. That's why no issue. The boiling point is very less, only 27 degrees centigrade. So while recording the spectra, what we are doing to the sample, we are adding tetramethylsilane. If you put tetramethylsilane at the room temperature, what happens? Automatically it can evaporate. So it's very easy or not. So the removal of the compound from the spectra is very, that's why we can use tetramethylsilane in most of the cases. But one of the disadvantages is there, tetramethylsilane is insoluble in water. But in our chemistry, we are having water soluble organic compounds. If you want to record the spectra for water soluble organic compounds, what are the water soluble organic compounds? Carbohydrates. If you want to record the spectra of water soluble organic compounds, we need to take the reference that should be soluble in water. That's why we are going to take the derivative of tetramethylsilane. See this one, sulfonic acid and its acid salts. Sulfonic acid is highly stronger in nature or not? That's why can easily soluble. So in order to record the spectra of these kind of molecules, we can use this kind of reference. So generally the reference is two types. Standard is two types: internal reference and external reference. Internal reference means what? Whatever the sample you have, to the sample directly add your reference. That is commonly called as internal standard. External reference means, so you have the sample here. To the sample we should not add the reference directly. You should take one tube and place your reference in that tube. That is called as external reference. So TMS is always used as an internal reference. Why? Because it can be easily removed. That's why we are directly adding. It cannot react with any sample protons. That's why we can use it as internal reference. Okay, it is readily added to the sample, right? So here it is, one of the example related to the calculation of the chemical shift values. You have benzyl alcohol. In benzyl alcohol, we are having OH protons and CH protons. Their chemical shift values are given, right? The instrument frequency is given. So what is the delta chemical shift value? This is chemical shift value in terms of edges. So what should we do? In terms of edges by instrument frequency, you will get delta chemical shift value. Similarly, toluene also. So here are the example. You can take this. Okay. What the people are saying, delta chemical shift values are always independent in nature. The delta chemical shift value or tau value cannot dependent on the strength of the external magnetic field or the strength of or the instrumental frequency. Here we have two words: frequency sweep and field sweep. This we will discuss during the discussion of instrumentation of NMR spectroscopy. Okay, so in the next class we will be discussing about what are the factors which can influences the chemical shift values. Okay, with this we will conclude the current session. Thank you very much.